Hi, my name is Caroline Jones and my group is doing the angle bisector theorem. The angle bisector theorem states, let AX be the bisector of angle A in triangle ABC. Then BX over XC is equal to AB over AC. In other words, X divides BC into two pieces proportional to the nearer sides, as shown in the illustration below. Before we get started with the proof, let us derive law of sines. In triangle ABC, the blue triangle ABC that is, capital A, capital B, and capital C all denote angles. And lowercase a, lowercase b, and lowercase c all are the sides opposite those angles. Let h be the altitude from angle A, and then we can see that sine of b is equal to h over c, and sine of c is equal to h over b, because when you take sine of an angle, you have the opposite over hypotenuse. H is equal to c sine of b, and h is also equal to b sine of c if we solve from h from those two equations. Then, since both of these measures are equal to h, we can set them equal to each other. So we get c sine b and b sine c are equal to each other. Then, if we divide both sides by sine of b and sine of c, we get c over sine c is equal to b over sine b. If we look at the pink triangle ABC, as before, capital A, capital B, and capital C all denote angle measures, and lowercase a, lowercase b, lowercase c all denote lengths of their sides, opposite those angles. In the pink triangle, though, we drew the altitude from angle B, but it's all the same process as we did in the first triangle. So we get A over sine A is equal to C over sine C from this triangle. And since A over sine A is equal to C over sine C and B over sine B is also equal to C over sine C, we can say that A over sine A equals B over sine B is equal to C over sine C.
Hi, my name is Brandon Conchaba, and before we start talking about the proof of the angle bisector theorem, let's talk more about the area of a triangle. So we know that the area of a triangle is 1/2 base times height. But there's actually another way to rewrite the form or the equation of the area. So if you look over at our picture, we have triangle ABC, and we've denoted the sides to be lowercase letters of the corresponding opposite angle. So side BC is lowercase a, side AC is lowercase b, and side AB is lowercase c. So we decided to draw the height from angle A down to BC, which is now lowercase a. So that makes our base A. So now we can go back, we can plug that in back into the area of a triangle and get 1/2 A times the height. So now remember when working back with law of sines, we know that the side of an angle, or the sine of an angle, is the opposite side times the hypotenuse. And so if we take angle B, you'll get sine B equals the height, which is the opposite side, over C, which would be the hypotenuse. So therefore, our height is actually going to be C times sine of B. So now you can plug that back into the area of a triangle equation for H, and you will actually get 1/2 times A times C times sine of B. Similarly, instead of taking angle B, you can take angle C and end up getting 1/2 times side A times side B times sine of C. And as you can see, the relationship, if that's the new equation for the area, you can see that whichever angle you take or to use for the area, then the two corresponding sides that you multiply will be the two adjacent sides of the angle that you used. So therefore, you can also get that the area can be 1/2 times B times C times sine of A. So now we can start the proof for the angle bisector theorem. So first we're going to draw our angle bisector from angle A. Therefore, that means that, as you can see in the picture, angle BAX equals angle CAX. And a reminder that the height of the triangle does not equal the angle bisector, which here is AX, because the height is going to be perpendicular from the angle that you draw it from. The angle bisector is not always perpendicular from the angle that you draw it from. So now that we've drawn the angle bisector AX, we now get two different triangles. We get triangle ABX and triangle ACX. So from here, to make things easier, we're just going to denote letters for the side lengths. So for triangle ABX, we're going to have side AB is lowercase c, side BX is lowercase d, and side AX is lowercase z. So now for triangle ABX, you get 1/2 times d times the height, since we've drawn the height from angle A. So now then, since we already derived another form of the area of the triangle, we're actually going to do that here for triangle ABX. So then we can also get, for the area, if we take it from angle A, we'll get 1/2 c times z times sine of A. So now we're going to look at the other triangle ACX, where we've denoted AC as lowercase b, and AX will be lowercase z, which will come into play later, and side CX as lowercase e. So we've drawn the height from angle A again, so therefore that will make our base E. So therefore we'll get one area equation will be 1/2 times E times the height. And then we can also, like in the other form, we'll take it from angle A as 1/2 times Z times B times sine of A.
Hello, my name is Paul Lee, and we will continue moving forward with the angle bisector theorem.
So if we combine parts 2 and 3, we know that the area of the left triangle ABX is equal to the area of the right triangle ACX. Using the two area formulas, the one on the left, 1/2 base times height, and then the one on the right, 1/2 sine theta times the two adjacent sides, we can actually set one area over the other. So if you look at the left side, 1/2 bx times h divided by 1/2 xc times h, they both have 1/2 h in common. So we can actually reduce that into bx over xc. And then if you look on the right side of the equation, 1/2 sine theta times the ABAX divided by 1/2 sine theta ACAX, we can actually reduce that also and get rid of the 1/2 sine theta AX, so you just have AB over AC left over. So finally we have BX over XC is equal to AB over AC. Alright, so on to a problem. So problem 1.13 says that suppose that in a triangle ABC, the median from vertex A and the bisector of angle A are the same line. Show that AB is equal to AC. So this is how we solve the problem. We know that angle BAX is equal to angle CAX because AX is the bisector of angle A. From theorem 1.12, we also know that BX over XC is equal to AB over AC. Right? Furthermore, since AX is a median, we know that BX is equal to XC since x is the midpoint of BC. So when you take bx over xc, that equals 1, so we can set 1 equal to AB over AC. So AB must be equal to AC.